Hi, this is the second video about capability ratio, and I'm working on problem 1 from page 15 and 16 on our chapter notes about quality control, and I'm gonna keep working on problem C, and the next step is to find the fraction that is defective, and to do that I have to find the z value associated with the upper specification limit, because this is the one that has the smallest number, which is selected for the capability ratio here. So the z value is going to be equal to, just to show you the formula, the z value comes from this here. The z value in the upper specification limit is this formula. This is what I'm going to do. So is equal to the upper specification limit 45 minus the mean. The mean is 41, okay, and I have to divide this number by not three times, just the sigma, just the standard deviation in this case is 1.5, because the variability increased from 1 to 1.5, okay? So that's my z value associated with this upper specification limit. Now I can use this z value to compute the fraction that is defective, and because it's upper limit and is a positive number, I have to subtract 1 minus norm dot s dot dist, select the z value, and then type comma, and then type 1, and then we have this fraction of defective parts, and the parts per million becomes this number here, equal this number multiplied by 1 million, 123, 123. So that's the defective parts per million, 3,830. Let's take a look at the notes. So this is C. We found these numbers here. Fraction that is defective is 3,830 parts per million. 3,830 parts per million. So we found the same answer from our class notes. Okay, so let's go to the last problem. The last problem is so before we move to this question, we have this question here: interpret this situation and propose a course of action. So what's happening here is we increase the variability in our processes. Now, so we are not only producing above the mean, filling boxes with more ounces of cereal, but also they vary more. These boxes vary more. Some boxes have more units and others have way less units. That's what the standard deviation is telling us. And when you take a look at the capability ratios, we see that this capability ratio here, that's the one that is really like affecting our process. This one generates 3,830 defective boxes every 1 million boxes. Okay, that's so many boxes that we have to throw away. Look how many sales we are losing here because they are defective. So we worked a lot, we have all these ingredients and everything, and we're throwing away almost 4,000 boxes. Okay. Remember that for the first two parts, this one here, the standard deviation is 1 and not 1.5. So a smaller standard deviation means that the boxes are very less. Because they vary less, the parts per million that is defective is way smaller than this one. Look, this one, the defective parts per million is 31 units, 31 boxes that are defective, each 1 million boxes. This is almost 1,000 times more. Okay, so you see how a small variability can increase a lot the money that we are wasting in the process. Okay, so we have to do something to reduce this variability and also to bring this mean to the center of the process. We have to work and then come up with alternatives to to reduce that, okay? So this is how we use this information. Now the process variability has been restored to a standard deviation or a sigma equal to 1, and the process mean is brought exactly to the target of 40 ounces. So we changed the process, we did like some adjustment, and now we have everything in place. Let's compute the CP and CPK of this process and see what happens. Okay, now we have everything on normal. So let's compute CP. Okay, remember our formula for CP is the upper, equal, so what I do is equal, open parentheses, upper minus lower divided by 6 times the standard deviation, which is here. So it's 1.67, okay? Now CPK. The CPK will have all these parts here. Let me put them here, okay? Let me compute. So this one is going to be equal to my upper minus, now my mu or my mean is 40. It's right on target. This is what the problem is saying, okay? And if I divide this number by 3 times the standard deviation, then it's 1.667. Now I do the same thing for the lower specification limit, which is my mean. My mean, I didn't take note about the mean here because the mean now is the same one as our target, so I'm not writing, but you have to know that now it's on target, minus my lower specification limit. And then I get this number and divide by, open parentheses, 3 times the standard deviation of 1. This is what the problem is saying. You see that now all numbers, they are aligned. When the process is centered, all capability ratios are equal, okay? So I can pick any one here, and it's going to be 1.6. So it's going to be any one. Let me get this one, okay? So let's see what else the problem says. Explain changes in both ratios relative to situation A. I explain what is the fraction defective now. Let's work on that. So as I told you, because the process is centered, remember it's centered because the process is now filling up boxes with 40 ounces and not with 41 ounces anymore, okay? So now is everything in place with the correct standard deviation. So to compute the fraction, I have to compute the z associated with any one of these two. Okay, let's use the low specification limit this time just to vary a little bit. So what is the z values? I could choose any one because both are equal. Let's work with the lower specification limit just to make something different. Let's take a look at the formula. So if we come here, the z associated is x is the mean minus, so is the mean equal the mean is 40 now, minus the low specification limit divided by the standard deviation of 1. That's how we compute the z associated with that, okay? Which is, just let me make sure, which is 5, right? And now what is the fraction that is defective? Remember, this is a positive number, so it's in the upper tail. Even if we're using like 2 tails lower and upper, the resulting number is positive, so we have to subtract from 1 minus norm dot s dot dist, this z comma 1, so that's the number, a very small number. But remember, this is only one of the tails. If I want to know everything, and this is what the problem is saying. Let's take a look at the problem. What is the fraction defective now? So the fraction defective now is going to be fraction, let's put fraction both days. The fraction in both days is going to be equal to 2 times this one, because this is only one tail. Okay, this is the fraction. You don't have to worry about this this weird number. This is a scientific number. This is a format. You could change the format here, but we don't need to. Let's leave like this because we're going to compute the parts per million. So the parts per million is equal to this number multiplied by 1 million. 1, 1, 2, 3, 1, 2, 3. So now we have less than one box, 0.57 of a box that is defective every 1 million boxes that we produce. You see how we reduced from 31 defective box per million to less than one box defective per million if the process is centered, is working according to what we designed to work, centered and with this standard deviation. So we have very few waste like money because we're only producing less than one box that is defective every 1 million. So we're saving a lot of money. Look the size of this reduction from 31 to less than 1. So only we produce a defective box only almost 2 million boxes. Okay, and if the process is not centered like in this case and has a lot of variability, we are wasting a lot of money. This is the reason quality control is so important for companies. That's a very good example. Okay, that's all for now.